Imagine electricity flowing normally through your home when suddenly a fault causes far more current to flow than the circuit is designed to carry. The wires can begin heating up, and if the problem is not interrupted, excessive current can damage equipment or create a fire risk. This is where a circuit breaker becomes important. But how does a small device inside an electrical panel detect a dangerous condition and stop the current? And how can the same device be switched back on after the problem has been corrected? What is a circuit breaker? A circuit breaker is an electrical switching and protection device designed to interrupt current when certain abnormal conditions occur. It is normally installed in an electrical distribution system between the power supply and the circuits that need protection. Under normal conditions, the circuit breaker allows current to pass through the circuit. When the current becomes too high for the protection setting or another specified fault condition occurs, the breaker operates and opens the circuit. Opening the circuit creates a gap in the electrical path. That gap stops the current from continuing through the protected circuit. Unlike a simple switch, however, a circuit breaker is designed to respond automatically to particular electrical faults. Let's first look at what happens when everything is working normally. Electricity enters the circuit breaker from the supply side. It passes through the breaker and continues toward the connected electrical circuit. Inside the breaker, conductive contacts provide the electrical connection between the incoming and outgoing sides. When those contacts are closed, current can flow through them. The connected circuit may then power lights, sockets, appliances, motors, or other electrical equipment. As long as the electrical conditions remain within the breaker's intended operating range, the contacts stay closed. The circuit therefore continues operating normally. The amount of current flowing through a circuit depends on the electrical load and the circuit conditions. A problem can occur when a circuit draws more current than its wiring and protective equipment are designed to handle. One common example is an overload. An overload can happen when too many loads are connected to the same circuit and their combined current becomes excessive. Another important fault is a short circuit. A short circuit creates an unintended low resistance path that can allow a very large current to flow. The exact response of a circuit breaker depends on its design and rating, but its purpose is to interrupt dangerous or abnormal current conditions before they can cause greater damage. How does the breaker detect excessive current? This is where the internal mechanism becomes important. Many conventional circuit breakers use thermal and magnetic protection. The thermal part responds to excessive current that persists long enough to heat a component inside the breaker. The magnetic part can respond very quickly to a large fault current, such as the current produced by a short circuit. These two mechanisms allow the breaker to respond differently to different types of abnormal current. The thermal mechanism. Inside a thermomagnetic circuit breaker is a component called a bimetallic strip. A bimetallic strip is made from two different metals joined together. The two metals expand at different rates when their temperature changes. When excessive current flows through the breaker, heat is produced in the current-carrying path. If the excessive current continues, the bimetallic strip becomes hotter. Because the two metals expand differently, the strip bends. As the strip bends far enough, it activates the breaker's trip mechanism. The contacts are then released and move apart. The circuit is interrupted. This process is useful for overload conditions because the breaker does not need to trip instantly for every small increase in current. Instead, the response depends partly on how much the current exceeds the breaker's intended range and how long the condition continues. The magnetic mechanism. The second major protection mechanism is electromagnetic. When current flows through a coil inside the breaker, it produces a magnetic field. As the current increases, the magnetic effect becomes stronger. During a severe fault, the current can become very large. The stronger magnetic field then acts on a mechanism inside the breaker. When the magnetic force reaches the required level, the mechanism releases the contacts. The contacts separate rapidly. This interrupts the fault current much faster than the thermal mechanism normally responds to a sustained overload. At this point, the purpose of the trip mechanism becomes clear. The breaker does not simply remove electricity from the entire building. It opens the particular circuit that it is designed to protect. When the contacts separate, the electrical path through that breaker is broken. Current can no longer continue through that protected branch under normal conditions. This helps limit the energy delivered to the fault. However, opening the contacts does not mean the fault itself has disappeared. The underlying problem still needs to be identified and corrected. What happens inside the contacts? When electrical contacts separate while current is flowing, the electrical path can briefly produce an arc. An arc is a visible electrical discharge that can form across the opening gap. Circuit breakers are designed with internal features to control and extinguish this arc. Many breakers use an arc chute containing specially shaped plates that help divide, cool, and extinguish the arc. The exact arc control design depends on the type and rating of the circuit breaker. The important point is that the breaker must safely interrupt the electrical current without allowing the arc to continue indefinitely. The trip mechanism. The trip mechanism is the part that converts the detection of an abnormal condition into physical movement of the contacts. The thermal or magnetic mechanism releases a latch. The stored mechanical energy inside the breaker then moves the contact mechanism. The contacts separate rapidly. The breaker handle may move to a trip position, depending on the breaker design. This gives a visible indication that the breaker has operated. Why does the handle not simply stay on? A circuit breaker handle is connected to an internal mechanism rather than directly holding the electrical contacts closed. This allows the breaker to trip automatically even if the external handle is in the on position. When a fault activates the trip mechanism, the internal latch is released. The contacts can therefore open without requiring someone to physically pull the handle down. This is an important part of automatic protection. After the breaker trips, the first step is not simply to switch it back on repeatedly. The cause of the trip should be identified. If the circuit was overloaded, reducing the electrical load may correct the problem. If there is a short circuit, damaged wiring, faulty equipment, or another electrical fault, that problem needs to be corrected before the circuit is safely restored. Once the fault has been addressed, the breaker can usually be reset according to its design and the manufacturer's instructions. When reset correctly, the internal mechanism closes the contacts again. Current can then flow through the protected circuit. Different types of circuit breakers. Not every circuit breaker operates in exactly the same way. Different breakers are designed for different electrical systems, current levels, voltages, and protection requirements. Thermal-magnetic breakers are common in many low-voltage applications. Other breakers use electronic sensing and control systems. Some specialized breakers are designed to detect additional conditions, such as residual current or ground fault conditions. The operating principle therefore depends on the specific type of breaker. Circuit breaker versus fuse. A circuit breaker and a fuse both provide electrical protection, but they operate differently. A fuse contains a designed element that melts when excessive current causes enough heating. Once the fuse operates, the fuse normally has to be replaced. A circuit breaker instead uses a mechanical switching mechanism to open the circuit. After the fault is corrected, many circuit breakers can be reset and used again. Both devices are designed to interrupt abnormal current, but their construction and operating methods are different. Now let's put the entire process together. Under normal conditions, the circuit breaker contacts are closed. Current flows from the electrical supply through the breaker and into the protected circuit. The connected equipment operates normally. If the circuit experiences an overload, excessive current produces increasing heat inside the breaker. The thermal mechanism responds when the condition persists sufficiently. If a severe short circuit occurs, the large current produces a strong magnetic effect. The magnetic mechanism can then release the trip mechanism rapidly. The internal latch releases. The contacts separate. An arc may form briefly as the current is interrupted. The breaker controls and extinguishes the arc. The protected circuit is disconnected. The cause of the fault can then be investigated and corrected. After the problem has been safely addressed, the breaker can be reset when appropriate. The contacts close again, and the circuit can return to normal operation. So, a circuit breaker is more than an ordinary electrical switch. It continuously carries current during normal operation while monitoring for conditions that can cause it to operate. When an abnormal condition reaches the breaker's operating threshold, its protection mechanism releases the contacts and interrupts the circuit. Thermal protection can respond to sustained excessive current, while magnetic or electronic protection can provide much faster response to severe fault conditions, depending on the breaker design. The result is a controlled interruption of the affected circuit rather than allowing the abnormal current to continue indefinitely. That is the basic principle behind how a circuit breaker works.